Welcome to the NPTEL online certification course on CMOS digital VLSI design. Let us start from where we left earlier. We were looking at the various problem areas of dynamic CMOS logic, and the third problem which we will be facing is basically known as capacitive coupling problem. So, the capacitive coupling problem, which is denoted here, we can see. So, the problem which we faced was that your output impedance, right, as I discussed with in the previous turn, that your output impedance is in the static CMOS logic is either connected to VDD or to ground. It is never kept in a floating node, whereas in this case during the evaluation mode you might have a chance at which your output node might be a floating node, right. It will not be a low impedance node available to you, which therefore makes it prone to a large amount of crosstalk noise, and therefore this is what is written here, that relatively high impedance of the output node makes the circuit very sensitive to crosstalk effects, right. In fact, if you are driving, for example, logic here by a dynamic logic which is kept here, even a small change here, for example, if this, let us suppose the switching threshold of M4 and M6, right, the switching threshold of this one is, let us say, some let us say 0.5 volts, right, and you are using a VDD of 1 volt, is it okay, and the output here actually out 1, let us suppose it falls down to less than 0.5 volts, then what will it will do is that this M6 and M4 will see a voltage here as interpreted as 0 rather than as equals to 1. This is the first problem. The second problem is, if you look at M4 and M6, M4 will have CGD here, which is this one, and therefore this CGD will add up with this CL1, and therefore the overall capacitive loading will also be large. You please understand therefore that if there is a capacitive loading between the clock at the PMOS and the output, which I discussed with you, I might discuss with you in the next turn when we do clock feed through, but you might have a case where you will have this clock at the pre-charge PMOS talking with your output here, right, and therefore if this CL1 gets added up with this capacitance here and here, the clock has to actually drive a heavy load, right, and therefore the clock power actually becomes very large. So, apart from the dynamic power dissipation of the system, your clock also gets loaded. So, the clock factor or the clock loading also increases drastically. So, what we are trying to look therefore is that, let us suppose you have entered into evaluation phase and clock equals to high, right, but A equals to 0 and B equals to 0. So, this out will actually hold its value equals to 1 here, right. If it is 1, it will actually obviously switch off M6, right, but it will switch on M4, right, and as it switches on M4, there will be heavy capacitive loading on CL1 and CL2, right. So, you might ask me that therefore, even if this is happening, since CL is not getting discharged, it does not matter whether it is getting charged or not. Very true, but then if there is a finite probability that A goes from 0 to 1, you still have no discharge. So, let us suppose A goes from 0 to 1, right. Then the charge which was located here will now be shared between this and this. So, there will be charge sharing phenomena taking place here, we will come to that later on, which means that if during the evaluation phase, right, your pull down network is not activated, even if part of it is activated, you might have a small chance that the charge accumulated at the loading capacitance might reduce due to charge sharing mechanism, and it might affect your overall mechanism of the thing. With this knowledge, let me come to the fourth problem of dynamic logic, and that is basically clock feed through problem. As I discussed with you in the previous turn, let us suppose I have a clock feed through. I will explain to you clock feed through. So, I have PMOS here, I have a PDN, right, I have a PDN here, and then I have an NMOS which is there, which is basically my evaluation. This is my pre-charge case, and this is basically the VDD which is connected here, and this is the output which you see. Now, if you look very closely here, this is basically a PMOS, it is basically a PMOS. So, PMOS primarily means that I have an N type substrate, right. I have a p type source or a p type drain, p type source in this case. So, if you look very carefully, if the clock goes high, right, ideally if the clock is not going high, it is typically at low stage or it is relatively low. So, let us suppose something happens here, right, it goes if there is a capacitive coupling between this point and this point here, the voltage here will also shoot up, right. And as a result, there might be a scenario where this p plus n region gets forward biased, and this is quite dangerous in terms of operation. So, whenever you have this phenomenon is not clock feed through. So, when clock which is given to PMOS gate actually does a capacitive coupling with the output side, you might end up having the reversed biased PN junction of PMOS actually converting into a forward biased PN junction, and therefore, a large current actually starts to flow. You are getting my point? Which means that though you did not want the PMOS to switch on, you still have a finite probability that the PMOS is switched on during that period of time. So, that is what we are talking about when we discuss here. So, an effect which is caused by the capacitive coupling between the clock input of the pre-charge device is what? The PMOS, and the dynamic output node. As I discussed with you just now, that the problem therefore is that normally reversed bias junction diodes of the pre-charge transistor will become forward bias, and therefore, there will be a problem in the operation. To show you that, look at this figure which is in front of you. If you look at this figure, this is time versus voltage. The blue, the violet or the blue curve is basically your clock, the green is basically your input, and you have got two output, out 1 and out 2, which is there, and I will explain to you what these are, and this is primarily because of the clock feed through. Now, let us look at when the clock goes. So, when you have evaluation phase, when you have evaluation, clock is low and your output is basically high, right. So, which is perfectly fine as far as understanding of dynamic logic is concerned, that when your input is your clock input is low, right, your output is basically high, and this is what you are getting here. As the clock starts to rise, you will have a push in the voltage here. So, the voltage goes slightly higher than the VDD value, right, and because of clock feed through, it goes like high. It remains high till the clock remains high, and then the clock starts, and then when the input starts to rise, the output will start to fall, because let us suppose A and B are both high and you have an AND gate available to you. Then when A and B are both high, the pull down network switches on, evaluation, you are into the evaluation phase, and therefore, the output voltage starts to fall down, and therefore, that is what is happening here. The output 1 starts to fall down, right, and this is what is happening here. Forget about this black curve, we will discuss that later on, but look at the red one, right. The red one actually does not even fall to 0. Why it does not fall to 0? The reason being that you did not, because some of the charges initially were lost by virtue of charge sharing or even by some other means. So, you had some decay of charge initially which you cannot recover, and therefore, the voltage does not actually go to 0 voltage in any of the situations. So, now you see what is out 1. Out 1 is primarily the voltage at the output of node 1, which I discussed with you earlier sets, and it even does not cross the value, it does not even cross the value of 0. Now, out 1 will, which means that the out 1 is the value of voltage when your clock is basically going high. So, your clock is still remaining high, you see this blue curve which you see in front of you, the clock is high, right. The clock is high primarily meaning my output should be actually falling down depending on the input. So, let us suppose your input was not high, in that case the output will be going down to below value. So, it should ideally latch to value equals to VDD, it does not, it falls to a value equals to out equals to 1, out 1. So, even in under the criteria that your A and B are both equals to 1 and you are designing an AND gate, output value of the voltage will not go down to 0, but slightly above 0, as I discussed with you now. This is the first scenario or observation. The second observation is that when your output is held at 1 and your inputs are actually given as 0 0 or 0 or 1 0, in either of the 3 cases the pull down network is not getting activated, and therefore ideally I should hold to VDD. In reality no, and therefore the out falls to out 1, which is slightly less than VDD, right. So, these are the 2 full scenarios available to you as far as this clock feed through is concerned, right. Another thing which I should include here before I move forward is quite interesting part, and people have been doing it quite often, is that I just now discussed with you that we are using a PDN, right. We are using a PDN here, and then I have got a PMOS here, and this is this, right, and this is this fine. I think it is clear to you. No, sorry, I am sorry, this and then this, and then this is there. The another concept is that, see, if I can simply make it something like this, that I have a PMOS here, I also have a PU pull up network, and then I take output from here, and then I have got the evaluation transistor. Just check it out that this will also work for me exactly in the same manner as this is working. These 2 are exactly the same, right. So, this is basically using NMOS logic, we are trying to find out the dynamic logic, and you can also use a pull up network to do it, but preferably we do the first one, which is using NMOS logic. Let me come to the domino logic here. Domino logic is basically what? An N type logic block. So, N type means you are making the PDN with N MOSFET, but that means you are not touching the P MOSFET. You can have P type when you have PUN on the pull up network with the Boolean expression. So, the Boolean expression is PDN here. So, we have one input, we have one PDN network here, and it is basically connected to a static CMOS here. So, I have a dynamic logic here, and it is cascading to a static CMOS logic at this stage, right, and that is what is known as a domino logic. And I will explain to you why it is known as domino. We can explain to you later on, but let me explain to you a basic thing here. Let us suppose your clock was going to 0. So, you are into pre-charge phase, output goes to 1, right, output goes to 1, this goes to 0. If this goes to 0, the PDN is cut off, let us suppose, because let me suppose that there are no input. So, input 0 is 0, and this goes to 0, PDN is 0. PDN is 0 primarily means that again this is 1, this is 0, again this is 1, this is 0. So, all the output of my domino logics are all in 0 state, fine. Now, let me do one thing, that let me say that my in 1, in 2, in 3 and in 4 are such that in evaluation phase that my PDN is on at evaluation. So, when my PDN is on in evaluation, this 1 goes to 0, and therefore, this 0 goes to 1. As this 0 goes to 1, suppose PDN goes on, as it goes on, this 1 goes to 0, and therefore, again 0 goes to 1. So, you see sort of a domino basically, if you remember, is basically small dominoes or small cubical structures which are kept in line. So, if you just push one of them, it's basically a cascading effect, and it pushes others in a row, right, that is known as a domino effect. Same domino effect happens here, that is the reason it is known as a domino logic, that you have a static inverter which converts it to a high logic. So, you see the advantage here, a static inverter output impedance is typically very low, and therefore, noise immunity is much better in a domino logic as compared to anybody else, right, fine. Not only that, the second thing is that since this is a static inverter, its noise margins are also very symmetric and high. So, NMH for this case will be approximately equals to VDD by 2 approximately, if you are assuming it to be an ideal NMOS device and PMOS device and CMOS transistors, then typically VDD by 2 is the typical sort of NMH NML which you get. So, the noise margins are typically very high, and as a result you will have a lower and means a lower signal, higher signal to noise ratios will be available to you. So, this was basically the domino logic diagram which I have showed to you. So, this is basically a PMOS NMOS followed by a static inverter. So, as I was discussing with you, the introduction of static inverter has an advantage that the fan out of the gate is driven by static inverter, which is basically at low impedance node, and therefore increases the noise immunity. So, that is one of the important issues has got there. Now, but you see the problem area. The problem area is, since each of the dynamic logic is cascaded with a inverter, the output of the inverter again is primarily a inverting mode. So, you will have an only you will have non-inverting mode can be implemented. You can always put another transistor, another CMOS inverter to invert it. Very high speeds, and the reason it is high speed is because the output load effectively sees only 2 devices or 3 devices at its output node, whereas in an inverter, static inverter, it sees all the transistors, CGD and so on and so forth. So, it is very high speed which you see, right. While interesting property here is that TPHL is actually equals to 0, right. TPHL is actually equals to 0. What is TPHL? It is basically high to low delay which you see, right. Now, high to low TPHL can only occur provided output was held at 1 and then you go from 1 to 0, but 1 to 0 can only happen in evaluation mode, and that too in the condition that the inputs are such favorable that the PDN is on or the pull down network is on, right. Under these two conditions you will have a 1 to 0 transitions, right. So, if this is not happening, your TPHL high to low will be always equals to 0, right. So, that is what I am trying to say, that you will have always equals to 0 here. So, these are the few properties of domino CMOS logic. One way to solve this non-inverting problem of domino logic is that you solve it by reorganizing the logic using simple Boolean transformation. For example, let us suppose you have this big circuitry with reconvergent fan out coming here, and final value is x and y, where x can be given by a, b, c, and your y will be a function of all a, b, c, d, e, f and g and h, right. Now, this whole thing, this yes, this is basically a domino logic. I can therefore convert this into a domino logic. I can take this and this together and have a domino logic, domino AND OR operation. So, this is basically AND OR, which is basically NAND operation, right, and this is domino OR operation because this is a NAND followed by a gate. You have a domino AND operation because you have a NAND gate available here, and therefore, you can convert a simple logic which is given by this into a domino logic, and you can still forward go with it, right. So, though we do not use too much of this domino logic nowadays because of the problem in terms of problems of cascading. Another way of doing is that we have already discussed this point earlier. It is basically DC-VSL logic, right. We have already done DC-VSL, where what we do is that we take the design and its complementary design, and then we run a positive feedback network in order to achieve the output results available to you. So, if you see here, for example, in this slide, you will see that A and B are in series here, but that primarily means that A and B will be parallel, A complement and B complement will be in parallel to each other. So, when you are into pre-charge phase, clock equals to 0, MP switches on, this goes to high, primarily meaning that your this transistor goes high, this transistor goes high primarily meaning that this feedback will be switched off. So, this will be switched off, right, this will be switched off. Once this is switched off, clock goes high, this is also equals to 1, right, this is also equals to 1. So, both are equals to 1 here, right. So, it is holding its state at 0 0, output is 0, input is also 0. Now, in the evaluation phase, depending on the values, so let us suppose A and B are both equals to 1, so this will not happen, nothing will happen here, nothing will happen in this case, but this will actually pull down the value of voltage from 1 to 0 here. At its pull down, MF2 starts to get on, right, MF2 starts to get on, and therefore, this one will do what. So, you see when both A and B are equals to 1, right, then A complement equals to B complement equals to 0. This primarily means that your this PDN2, right, is off state, whereas PDN1 is basically non state. When this is on state, it tries to pull the transistor or the voltage from here back to the ground, because my clock is 1, ME is on, and therefore you have a direct path between this to the ground, and therefore it falls down 1. As it starts to fall down to 1 and it crosses the mod value of the threshold value of MF2, when MF2 is this transistor, then this switches on, right, and therefore this VDD which is kept here will try to charge up this node. So, even if this node actually has some delay or some leakages, will be actually compensated by this VDD actually trying to pull up this value. So, this falls to full of AB. So, this becomes equals to 0, and this is basically equals to 0 to 1. So, this becomes 1 here. So, I have 1 here and I have a 0 here, right. In the next phase, when you go to pre-charge, again the same thing happens, that you are able to sustain this to again to 1, and this again goes to 0 again. Is it okay? So, this is an why I say it is an expensive proposition, because when you use a DCVSL you actually end up having larger area. So, the advantage which you got out of domino logic, you are actually losing in terms of this DCVSL, right. But the idea is typically very good, where you use a dual voltage supply here, fully differential output to be available to you, right. So, this is one thing which you should know. Let me end up this dynamic logic course with what is known as an NP-CMOS. So, what I told you was that I can therefore replace the PDN by having a PUN, and this is basically cascading N tree with P tree. So, if I have a NMOS here, NMOS based PDN, right, and I have a PMOS in the pull up network, and if I simply cascade these two together, then I get what is known as a dynamic logic or an NP-CMOS logic. So, this is basically NPY, because this is an N, this is P, because this is made up of PMOS, this is made up of NMOS, right, and you will have dynamic NP logic available to you. It has got its own advantage, but generally PMOSs are not used, NP logic is not used, NP-CMOS logic is not used, because PMOS's mobility is typically very small. So, the delay is relatively very large in case of PMOS, right, and therefore, though your NMOS will have a smaller delay, but you will face a problem of latency when you come to the second figure, which is this PUN figure, right, and there will be a problem in terms of latency, or the signal has to wait in certain period of time in order to do certain job, right, and that is the problem area of NP logic. With these definitions understanding, let me recapitulate what we have learned in dynamic logic. So, this till today what we have learned is we will finish off our dynamic understanding of fully combinational logic. From next time onwards we will start with sequential as well as logical efforts. As I discussed with you, dynamic logic is divided into two phases, one is known as pre-charge, another is known as evaluation. Pre-charge is one when the clock is low and your PMOS is switches on, and therefore, the output node is charged by VDD to 1. What is the evaluation phase? Evaluation phase is when clock goes to 1, your pull down transistor ME, which is the evaluation NMOS transistor, switches on, and depending on the values of A, B, C, D, the input I can have either a 1 to 0 transition, or my output node switches to a floating to a low impedance node, and it holds the value of 1 there. We do have a problem of 4 things, especially in terms of signal integrity issues: charge leakages, charge sharing, capacitive coupling, and clock feed through. So, these are the 4 basic problem areas of this thing. In all the 4 cases, there is a drop in the voltage in the output, which results in a smaller value of voltage in the output. As I discussed with you, to increase the noise immunity, the domino logic is proposed, which consists of a static inverter and dynamic. So, I have a static and a dynamic, both of them are cascaded to form a domino logic. Finally, we saw an NP-CMOS logic where my pull up network was basically by PMOS and pull down network is primarily because of NMOS, right. So, this is what we have learned till now as far as combinational logical block is concerned, and we have also learned various aspects of combinational logical block, and next time onwards we will start with either sequential logical block and we will see how it works out fine, right. With these words, I thank you all for your patient hearing, and thanks a lot. Thank you.